Okay, so let's get started with the 118B midterm review session. Do you guys want to start with the new material, chapter 17, 18 stuff? Okay, let's do that first. Okay, I'm just gonna start from the very beginning, explain everything in general, go over all the reactions, mechanisms, and then we're gonna do practice challenge after that, right? So chapter 17 here is gonna have a common mechanism called nucleophilic addition, right? And we can have that in basic conditions and acidic conditions. So the common mechanism is that when we have this carbonyl here, right, this can react with some. Wait, am I doing the right chapter? Like nucleophile, hemiacetal, acetal. This is the hemiacetal acetal chapter, right? Chapter 17 for 118B. Okay, okay. Yeah. So this is basic conditions because we have a negatively charged molecule here. This could be OR or OH minus. This is going to be my starred carbon or whatever it is, oxygen. And this right here, this carbon is my electrophile. So this nucleophile here is going to attack that carbon, pop the double bond onto the oxygen to conserve the octet row, right? So when we do that, we're going to get this right here, this tetrahedral intermediate where we have an O minus and a nucleophile. Now for 8B students, once you have this O minus, right, you're not going to reform the carbonyl and kick out a leaving group, because if you reform the carbonyl and kick out that nucleophile, you're going to go backward, right? But let's say you had a leaving group here, like chlorine, right? The acyl chloride, the most reactive derivative. You can actually reform that carbonyl and kick out the chlorine right there. That's for the carboxylic acid derivatives for 8B. But for 118B, because this is a tetrahedral intermediate where we don't have any other good leaving group, the next thing we would do is we could use the solvent to protonate the O minus to become this neutral OH right here, right? It could be the solvent here, or if you have a second step of acid workup like H3O plus, that H2O plus would protonate the O minus as well, right? Now in acidic conditions, let's have the same carbonyl, but this time we have a neutral nucleophile with a strong acid, H2SO4. This carbonyl carbon here is an electrophile, but it's a weak electrophile. This neutral nucleophile here is stable, right? It's very happy right now because it's not charged. And because it's very stable and happy, it's less reactive. It's a weak nucleophile. So if this acid was not there, this would be no reaction. This nucleophile cannot attack that carbonyl carbon. So the first step here is to protonate the carbonyl oxygen with the strong acid we have, H2SO4, right? And that's going to activate the electrophile, make the electrophile stronger. Right? Now, once you have this positively charged carbonyl here, this carbonyl carbon now has a bigger positive charge because this is a very angry oxygen now. This oxygen does not want that positive charge at all. So what it's going to do is that it's going to withdraw electrons from the carbon, making this carbon more positively charged, more electrophilic. The next thing here is that we're going to have the neutral nucleophile to attack this strong activated electrophile, right? Before, this nucleophile was not able to attack that carbonyl carbon right away because it was weak. Once we activated it to make a strong electrophile, we can attack that carbonyl now with the weak nucleophile. And that's going to give us this tetrahedral intermediate here, where the nucleophile here is going to tend to be positively charged. Like imagine this was H2O, and this is the oxygen atom here. This would be the oxygen atom that is now positively charged because it's going to have 3 bonds, right? Now, the last step here is to deprotonate this positive charge with the base, which is going to be HSO4 minus, right? And that's going to give us our final answer right here, okay? Any questions on the mechanisms for basic conditions or acidic conditions before I move on to hemiacetal and acetal formation? Yes. So the activating part again, this is a weak electrophile. This is a weak nucleophile. Weak cannot react with weak. So this nucleophile here cannot attack the carbonyl right away. What we have to do is that we have to use this strong acid here to protonate the carbonyl oxygen, right? This carbonyl oxygen here grabs the hydrogen from H2SO4 and kicks out an HSO4 minus. When we do that, we get this protonated carbonyl here. Think of this protonated carbonyl as a strong electrophile because of this angry oxygen here, making this carbonyl carbon way more positively charged because the oxygen is going to want to withdraw electrons from the carbon even more, making this carbon more positively charged. And because this is now a strong activated electrophile, this weak nucleophile can then attack the strong activated electrophile and pop the double bond to the oxygen, giving this tetrahedral intermediate. Whereas this is the neo bond right here that we made between this carbonyl carbon and this nucleophile here. If this is my dot carbon, this is my star carbon, this is the neo bond between the star and dot carbon that we formed. This single bond OH was from the carbonyl right there. The last step is to neutralize and deprotonate the positive charged nucleophile with the base HSO4 minus to get that neutral product right there. Right. This is going to be the mechanism for hemiacetal formation, acetal formation, imine formation, enamine formation. Right. I just want to go over this general mechanism first because these mechanisms here are going to be the same for all those reactions. The only difference is what nucleophile you use. For hemiacetal, it's going to be OR. Acetal is also OR. Imine with the I is primary amine. Enamine with the E is going to be secondary amine, right? So I'm going to go over all that, but this is just like the general mechanism for all those reactions right now before we jump into those reactions. Okay. Yes, sir.
What happens if there's no H2SO4?
Yes, if there's no H2SO4, let's do this in a different color. No reaction. I've seen some problems from Lieben's worksheets where she puts an amine here and a carbonyl here, and the product was an imine, right? But that's gonna be with a pH of 4 to 5, slightly mild acidic conditions. But for helix's purposes, for 118B, you need that strong acid for it to go through for helix class. So don't worry about that for Lieben's class. Yeah. Okay. Any questions on this general mechanism before we hop onto hemiacetals and acetals? This acidic conditions here, you would always have a weak nucleophile. And this weak nucleophile here, it can be H2O, ROH, RNH2, or R2NH. These is going to give you a geminodiol or a hydrate. This is going to give a hemiacetal or acetal. This is going to give an imine. This is going to give an enamine. That's what I'm talking about here. Like the exact same mechanism, just different nucleophiles. And depending on what nucleophile you use, you're going to form a different product, right? Hydrate, hemiacetal or acetal, imine or enamine. But we'll go over all those one by one for this chapter. Okay. Now, yes.
So enamine is a molecule with this nitrogen connection to 3 different carbons.
Enamine is a nitrogen next to an alkene. Enamine, alkene next to amine. Enamine. It's like enol, right? Enol, alkene next to alcohol. Enol, enamine. And chapter 18 is going to talk about the alpha carbon of the enol and enamine and how you could alpha alkylate that for chapter 18. So keep that in mind for when we go over chapter 18. Okay. Yes. Now let's go over Hey, Cyrus. Hemiacetals and acetals. Right. So an acetal is going to have a carbon bonded to two OR groups. A hemiacetal is going to be a carbon bonded to one OR group and one OH group. So hemiacetal is half of an acetal. Hemi meaning half, right? Half OR, half OH. An acetal is more stable than a hemiacetal. Now, I'm going to show you the mechanism on how to create the hemiacetal. And the hemiacetal can only be formed, well, actually it can be formed in basic and acidic conditions, whereas the acetal can only be formed in acidic conditions. Right. So let's talk about the basic conditions first. All these ketones here or carbonyls here are going to be very basic because I'm just going to go over the general reaction mechanism. But everything else, like other problems that you see with like tert-butyl groups, rings, benzenes, those are distractions, right? They're going to confuse you, but just keep in mind the actual chemistry that's going on. It's going to be this carbonyl here, and everything else, like tert-butyl, sec-butyl, isopropyl, are distractions. Let's say we have this ethoxide here with that solvent in basic conditions. What do you guys think is going to happen here between this molecule and this strong base, strong nucleophile here for this chapter? Right, this is going to follow the same mechanism as we did earlier at the beginning of the session. Right, nucleophilic acyl addition. Acyl is a carbonyl. Carbonyl, this is an acyl group. Right. If this is a carbonyl carbon here, and this is my nucleophile here, the O- is going to attack the dot, pop the double onto the oxygen, and create this intermediate here. We have an O- here. This is the dot carbon. This is going to be the nil bond between the dot carbon and star carbon right here. Or star atom here. Right? This oxygen here is that oxygen right there, which is attached to an ethyl group, like that. Right? The next step here is to protonate the O- group with the proton source, the ethanol right there. And that's going to give us this structure here, which we see is a hemiacetal, right? Because this carbon here is attached to one OH group and one OR group. In acidic conditions, if I have that carbonyl here, I'm not going to have a negative charged molecule. It's going to be neutral with strong acid here. So what's going to happen first is that this is not going to react with that right away. We're going to have to activate this carbonyl, make this a stronger electrophile by protonating it with the strong acid we have here present, H2SO4. Right? When we do that, we're going to get this strong activated electrophile right here. This is now a strong enough electrophile for this weak nucleophile to come in, attack that carbonyl right there, pop the double onto the oxygen, and give us this intermediate here. Right? And keep this in mind, we still have the R group of the oxygen attached to that oxygen. The hydrogen is still attached to that oxygen. And because this oxygen has 3 bonds, it's positively charged. Right? Now, the last step here, if you want to stop at the hemiacetal, is that we're going to deprotonate the positive charged oxygen to give us our neutral hemiacetal. OH, OH. And this is if we have only one equivalent of the alcohol, but most likely you have excess amount of this alcohol, and this is when you can go all the way to an acetal. But I'm going to stop here for now because this is just forming a hemiacetal in acidic conditions and basic conditions. But we're going to come back to this when we go over acetal formation. Yeah. Oh my gosh. Yes. Any questions on this mechanism? Right. Yeah, so this is going to help 8B and 118B as well. Okay. Sorry.
This is more topical compared to the bottom.
Mm-hmm. Not the hemiacetal though, because I'm going to go over a conceptual thing after I go over the acetal.
Yeah.
Hemiacetals are not very stable,
Yes.
right?
Acetals
Acetals, more stable.
Yes.
So the product is most likely going to be acetal. Yes.
Oh.
Hemi is partial. Yes.
So synthesis.
Mechanism. Yes, mechanism.
It's like maybe stop at the hemiacetal. They might like make it one of those
Uh-huh.
stop at the hemiacetal position.
Yeah, it could be explanation as well. Like when you talk about stop at the hemiacetal, why do you stop? Why can't you go forward to the acetal in basic conditions? Yeah. So explanation or mechanism problem. You can see this on.
Thank you.
Yes.
So just for clarification, in the formation of hemiacetal, the original carbonyl becoming OH?
Yes, the original carbonyl becomes the OH group for hemiacetals. These OH groups here came from that carbonyl right there.
And including adding alcohol, becoming like an alcohol group attached to the OH?
Yes, the alcohol group or alkoxide group becomes the OR group of the hemiacetal. Right, this OR group came from this alkoxide. This OR group came from the alcohol. Yeah. Yes, Jenna? For basic conditions, this RO minus, yes. This ROH here is the proton source. So when we grab the hydrogen from the OR, we kick out an RO minus. Right, so that's the side product, RO minus. And for leavings especially, you have to draw that RO minus out for mechanism. That will count as points for mechanism for leavings. Oh, you're thinking about Claisen condensation. That's not this. Yeah, yeah. No. That's 118C. Yeah. This is 8B, 118C. Don't worry about that. Yes. Yeah. But when I come around to answer your guys' questions, and you guys are 8B, I could go over more about Claisen condensation for 8B students here. Okay. Yes.
My notes say like hemiacetals could be only isolated in acidic conditions.
Can only be
isolated
isolated.
in acidic conditions by removing H plus floating around, which could stop it from keep going and form an acetal.
Acetal. Yes. If I'll go over that concept after. Yes. When hemiacetal can be isolated and when can it not be isolated. Yes. Okay. Let's move on to the acetal one. Right. Okay. So for acetal, when we have this carbonyl here, and we have 2 equivalent of the alcohol in acidic conditions, the first step, activate the carbonyl. Because this is in acidic conditions, we protonate the carbonyl oxygen, creating this strong electrophile, which then allows this weak nucleophile alcohol to attack the carbonyl carbon, pop the double bond onto the oxygen, and get this tetrahedral intermediate here. Right. Now, what do you guys think the next step is going to be from this intermediate here once we get that intermediate. Yes. Yes, this hydrogen will be removed by HSO4 minus that we formed in the first step. So the HSO4 minus comes back to grab that hydrogen and neutralize that positive charge oxygen. Right? And what did we just form here? What functional group is this? Hemiacetal, yes. We don't stop here because we have 2 equivalent of the alcohol. If you have 2 or more equivalents, excess, you keep going all the way until you get the acetal. So for predictive product purposes, if you want to predict the product quickly, this is what you do. This is your carbonyl carbon right here, which is that red carbon right there. Because we know this is an acetal, the 2 OR groups coming off of that carbon is going to be the OR group of the alcohol like that, right? The OR group of the alcohol is OCH2CH3, which are these OCH2CH3s, OCH2CH3s like that. So this is our end goal. So we want this group to leave, but right now it's a bad leaving group. How can we convert this bad leaving group into a good leaving group? We want to make it water, into water. And to make it into water, we have to protonate it with a strong acid, H2SO4, to make it into water. Right? Now, once this is a good leaving group, we could drive that good leaving group off by forming a carbonyl with this oxygen and kick out that water, giving us this intermediate here. This H2O here came from that water group that left right there. This is an activated carbonyl because this carbonyl oxygen is positively charged. This is when we bring in the second equivalent of the alcohol to come in and attack the carbonyl carbon right here, pop the double bond onto the oxygen, and give us our final intermediate. Right? And the last step here to get to the final product is to deprotonate the positive charge oxygen with HSO4 minus to get the neutral oxygen. Like that. And this gets our acetal. Yes?
I don't understand like how the double bond works.
This double bond here came from that pair of electrons on oxygen right there. It went down to make a double bond between carbon and oxygen, which is going to give this carbon 5 bonds if we don't do anything else. 1, 2, 3, 4, 5. To conserve the octet rule, we have to kick something out. And because we just formed a good leaving group here, we kick that good leaving group off, which formed this carbonyl here and the water that left as a leaving group.
Okay.
Yes. Why for acetal every step is reversible, but not for hemiacetal?
Yes. For the reversible mechanisms, there tend to be in acidic conditions, right? And the irreversible mechanism is going to tend to be in basic conditions. For hemiacetal, you can draw the two-sided arrow if it's in acidic conditions, right? But if it's in basic conditions, like you have the RO minus, it's going to be irreversible. And the reason why is because if I have this carbonyl here and I have this base here with the solvent, and I attack this carbonyl carbon here and push that up there, I do not draw the reversible arrows here. I draw the irreversible arrows going forward only, which gives me this intermediate. And the reason why it cannot go backward is because if I try going backwards, right, by reforming the carbonyl, I cannot kick out this leaving group. This is a bad leaving group. That's why I can't go backward. But if you see in this case, once this alcohol attacks that carbon, this is reversible because we can actually reform the carbonyl and kick out this leaving group. This is a good leaving group. And because this is a good leaving group, we can actually go backward here, making it reversible.
So how's the other one? Water and or their pros are bad.
This one.
Yeah. Also
So this is reversible because this is talking about this state to this state here. We can go from here to here by protonating this OR group with the H2SO4, which will go backwards to here, right? We cannot go from here to here, right? Because we can't kick that out and like we can't reform the carbonyl here and kick that out to go all the way to here, right? That's why it's like step-by-step mechanism. We can go from here to here though. That's a good question. Yes. Oh, we needed to use H2SO4 again to convert this bad leaving group into the good leaving group oxonium ion, which is going to eventually lead to water, right? Because we want this group to be gone eventually because we don't have the OH group in the product. So to make this into a good leaving group, we use acid to make that into a good leaving group. Yeah. Yes. Oh, it can leave. If we reform the carbonyl here, like this is like, it can happen, right? If we reform the carbonyl and kick that out, that goes backwards to here. We're gonna get this ROH and carbonyl again, so that can happen. I wouldn't say the more favored reaction because this is gonna lead to the more stable product here. The productive step, right? We're in acidic. We want to go forward and make something new. Yes, this right here, when you do reform the carbonyl and kick out the leaving group, that's an unproductive step because you're not making anything new. You're going backwards to the old material, right? That can happen, but to draw out the new mechanism, we're gonna do this instead to draw out the new mechanism. Yeah. Okay. I used HSO4 minus. HSO4 minus. Yes. Yeah. You could use alcohol or HSO4 minus to deprotonate. You could use either or. Yeah. Yeah. But if you use HSO4 minus, you're gonna reform the acid catalyst because in catalyst, the mechanism, the catalyst gets reformed, right? But you could use alcohol as well. Yeah. Okay. Yes.
You might have explained it already, but why is it that the acetals can only be formed in acidic conditions?
Yes. In acetal, we can only form it in acidic conditions because if we're in basic conditions, we cannot turn this into a good leaving group. We need the acid to convert it into a good leaving group to go all the way to the acetal. Yeah. So that might be an explanation problem right there. Yeah. Yes. If it says one equivalent, you would stop here at the hemiacetal. Yes, if it says one equivalent. Okay.
Could you go over the formation of geminodiol?
Geminodiol, yes, I will go over that after I go over the concept of when hemiacetals are isolatable and when they're not isolatable. Right. Okay, moving on. Okay. So you know how when we have a carbonyl here, we can create the hemiacetal in basic conditions or acidic conditions. I'm gonna draw the arrow, right? Actually, I'm gonna draw this actually first right here. In both mechanisms, this carbonyl carbon is the electrophile. The ketone here is the weakest electrophile because there's two R groups donating electrons to the carbonyl carbon, reducing the positive charge character of that carbonyl carbon. This is going to be the biggest electrophile because there's an electron withdrawing group withdrawing electrons from this carbonyl carbon, making that carbonyl carbon bigger positive charge. This is going to be right there. This is going to be right here. right? Because this hydrogen here is not an EDG, electron donating group. It's not an EWG, electron withdrawing group. So it's not going to have any effect on that carbon-carbon positive charge character. This R group here is donating electrons to that carbon-carbon, which is why this positive charge is smaller than that positive charge, right? Now, when you try to form hemiacetals, when you have a ketone, the carbonyl is favored. The reason why the hemiacetal is not favored is because this is a weak electrophile. It doesn't really want to go towards the hemiacetal. When you have these two reagents here, the hemiacetal is favored because they are electrophilic enough to proceed with the mechanism towards the hemiacetal. When you have an aldehyde, 1-to-1 ratio between the carbonyl and hemiacetal. Yes. The starting material from a carbonyl to hemiacetal, right? Because the hydrolysis of hemiacetal, this would be the product. Because you could actually go backward from a hemiacetal to the carbonyl. So this right here I'm talking about are the reactants, right? If you have a ketone as the reactant, the carbonyl form is favored. Yes, with one of these. Another thing that I want you guys to know are cyclic hemiacetals. They are isolatable, right? That's going to be something like this, right? Where this carbon here is attached to an OH group and OR group. This hemiacetal is actually stable enough to exist. And if it's stable enough to exist, we can isolate them in lab. So this right here is isolatable, right? When the hemiacetal is favored, that's also isolatable. This one right here, the hemiacetal, would be unisolatable. We cannot isolate that in lab because the carbonyl form is favored, right? So those are the conceptual questions on when hemiacetals are isolatable versus when they are not isolatable. Yes. The cyclic hemiacetals are isolatable because intramolecular reactions are very stable, very fast, right? So this ring right here is like a stabilizing factor, making it more stable than linear hemiacetals, right? So that's a conceptual thing that you need to know. Yeah. And it has to do something with entropy and thermodynamics, but you don't have to worry about that. Just know that the cyclic hemiacetal is more stable than linear hemiacetal. Yeah. Yeah. Oh no, they're a separate category. Yes, separate category. Yeah. Right. More stable. Something about increased entropy from intramolecular reactions. An example that would create that is going to be that right there in, you can say, basic conditions, right? NaOH, H2O, which is going to deprotonate this alcohol to create the O minus, and the O minus would attack that carbon, push it up there, and it gets protonated to form this right there, right? And this right here is going to be isolatable because this is a cyclic hemiacetal right there, right? Like if this is atom 1, 2, 3, 4, 5, 6, that's this atom 1, 2, 3, 4, 5, 6 right there. And we're making a new bond between 1 and 6. That new bond is formed from when we deprotonate this OH to become O minus. O minus attacks 6 to create that new bond right there.
So how the one of the carbonyl?
Yeah, you could number this 1, making this 6, but keep it consistent when you do the mechanism, your numbering system. You could also number this 1 if you wanted to. Yeah. Yeah. Yes, isolatable. It's more of a helix thing. Well, I see Levens went over this as well for 8B. Isolatable meaning that we can put this in the container in lab. Like when we
stable enough to exist in its own form. It won't like go full further to make a acetal.
yes, it won't go backward.
Forward back.
Right, because if we try to make a hemiacetal right there, this right here we cannot contain it.
Not a stable product.
Yeah.
Where would that end,
Yeah.
right?
So it's gonna go here. Yeah. Right. Nice. It's a lot. What time is it? 4:07. 5:30-ish. Okay. Ish. Yes. So that's hemiacetal, acetal, hydrate formation, right? Yes. Isolatable, you can go back, but it's not as likely to go back because this form here is more favored, so it's more likely to not go back. Yeah, more likely to not go back. Yeah, more likely. Yes. This last structure here, chloroform something. I don't know the name of the structure. Sorry. Oh yeah, Levens makes you know the molecules for sure. I will look through the notes and see what she named this. I don't know the name of that.
No, it's not even formed because you have
Chloroform.
it's attached to that one.
Oh,
You have to have CHCl3, right, for chloroform.
oh yeah. CHX3 for chloroform or
Yeah.
haloform. Yes.
Yeah.
Uh-huh.
That's the only thing I know.
Nomenclature. Don't spend too much. I didn't spend too much time on nomenclature. Yeah. Hydrate formation. Okay, let's go. Hydrate, aka geminodiol. That's when you have a carbon attached to OH groups, like that. Same mechanism. Basic and acidic. So we have that right there. NaOH, water, oxygen, H2O, H2SO4. Okay? Do you guys want to try this on the board? Someone write the mechanism and predict the product. It's the exact same mechanism, right? It's just a different nucleophile. Exact same mechanism for nucleophilic acyl addition in basic conditions and acidic conditions. Okay. Yeah. Yeah, try it for now, and then I'll go over this later. Yes.
Electrophile, is that like to form both a hydrate and an acetal or hemiacetal? Interactivity. Oh, so
Yes.
either one.
Yes, either one. Yes.
Okay, cool.
Yes, that's a good point actually. When I was talking about the electrophile and when things are isolatable and versus unisolatable, it works with hydrate and geminodiol as well. It's the same exact group, right? Because hydrates or geminodiol, they're very unstable, just like the hemiacetal. But we can isolate them in those reactions I gave you guys earlier with the EWG and what was the other one? EWG. So it was a ketone, aldehyde, a formaldehyde. Yeah, formaldehyde, yes. The formaldehyde and the EWG would make this isolatable. Yeah. Yes. Here you go.
And it's like the similar thing to acidic.
Water can attack that right away, but we have to do something first.
Because like this will attack the hydrogen here. Or...
This would get protonated by the acid, making that a strong electrophile.
Gotcha.
And then once it's a strong electrophile, the neutral water can then attack it and pop that up there, and then deprotonate the water to get the hydrate.
Okay, gotcha.
Yeah. Yes. Mm-hmm. Want to draw that mechanism down in the acidic conditions of the board? No? Okay, okay. It's okay. It's okay. Because people have the make the same mistakes too, so it's okay. Yes. So for basic conditions here, this is a strong enough nucleophile to attack this weak electrophile directly, creating this intermediate, and then this carbonyl becomes O-, which becomes protonated by the solvent water to give us our hydrate. That's it. Nice. Yes. Can this water attack this carbonyl right away? No, because this is weak. This is weak. What can we do to make the reaction go through? Protonate the carbonyl, which gives us this here. Now, can the water attack this carbonyl? Yes. Pop that up there. Give us this intermediate. What's the last step to get our deprotonate? And that gives us our neutral hydrate. But like I said earlier, these hydrates or geminal diols here are unstable. They're typically unisolatable unless we're like given this or this, right? And in the last example, I made this a methyl group, but it's supposed to be an aldehyde, so then there's no EDG on this carbon right here. Because if there was an R group there, that might like cancel out the effect of this EWG. So keep that in mind. Yes. The reversible arrows. For helix, he's not as strict as Missouri. Missouri would take points off if you don't do reversible, irreversible arrows, but helix would accept like if you do front and back or not. Yeah. Basic conditions, yes. Acidic conditions, reversible. Basic conditions, most likely irreversible. Throughout the whole thing. Uh-huh. Oh, sorry. Yeah. Yes.
Question for you. So I draw the resonance structure out for carbonyl, you know, to go into this negative positive here. Is this a valid way of looking at it, or is that not true to form, like of what's actually going on? Instead of having a triple bonded, you know, like an O with tree bonds.
Yes, this is a valid way to look at it, but this positive charge carbon here is stabilized by this neutral OH.
Yes.
Right there. So this water here is not able to attack the carbonyl right away, just yet, right? But if we protonate the oxygen with the positive charge right there, this oxygen would also have a hydrogen with a positive charge. That makes this molecule more unstable. Right, and because of that, this water is not able to attack that unstable molecule.
This wouldn't happen.
Yeah, this wouldn't happen because this is stable. This is
as is with the carbocation on there. Yeah.
Yes, right.
Okay.
And with only one form of charge, so this would actually not happen here. Yeah. If you wanted to make it happen, then you would want to protonate the oxygen and then have it attack.
And then you'd have like a leaving group, and then right.
We would then end up with this.
Oh, okay.
Right, because when we have this oxygen positive charge right there and water attacks.
Well, this is protonated, no?
Oh, it is protonated.
Yeah. You know what I'm saying? All I did is I just attacked it while I was in this form.
Oh. Yes, that's
works,
good. That's
right?
good. That works.
Okay.
Yes. Nice. That's a different way of doing it. Yeah. Yes. That's good.
Thank you.
Okay. So there's Imines, Wittig reaction, Baeyer-Villiger reaction, and then the two tests for aldehydes, Fehling's test and Tollens test for chapter 17. Is there anything else for chapter 17 that I'm missing? Wittig is the one with the ylide, the phosphorus pH3, and carbonyl to create the E or Z alkane. Baeyer-Villiger is the peroxy acid with the migratory aptitude. The Fehling's test, Tollens test is in there. Enamine is in there. Is there anything else for chapter 17? I want to make sure I go over all of chapter 17. Yeah.
A mechanism?
No. It's more for predictive product, but because you went over the mechanism, I would include it in your chart, in the note card. Yeah. Yes.
Is there such thing as intramolecular one equivalence?
Intermolecular one equivalence with hemiacetal formation? Yes. Yes, yes, yes. Uh-huh, yes. Okay. There's 3 more major reactions for chapter 17 I want to go over before moving on to chapter 18. Okay. Any questions on this before I move on? Okay, let's go. Okay. So the next thing I want to go over is amines and enamines. So I didn't go over the hydrolysis reactions and mechanisms, which is the reverse, right? Going from a hemiacetal, acetal, hydrate, going backwards to the carbonyl. But if we have time at the end, I can go over those mechanisms because all these reactions, because they're reversible, he could test you on that reverse mechanism. Like he could start with the acetal, especially intramolecular acetal, right, and go backwards to carbonyl. So if we have time at the end, I'll go over that. But let's first go over imine and enamine. An imine is when you have a carbon double bonded to a nitrogen that is attached to a hydrogen or R group. An enamine is when we have a carbon bonded to a nitrogen with 2 R groups and alkene nearby like that, right? Enamine, alkene next to amine. It's like the enol, but instead of an alcohol, we have an amine. And these mechanisms here are going to be for leavens around pH of 4 to 5. For helix, H2SO4. So if I have this carbonyl here, and I'm going to stick with helix's mechanism, which is going to be the same mechanism for leavens, but leavens might not give you an acid. She might just give you an amine, right? To form an imine with a carbonyl, your nucleophile is either going to be the ammonia, NH3, or primary amine, RNH2. To form the enamine, you need a secondary amine, R2NH, or R prime H, right? Because these R groups can be different. They don't have to be the same. But these two are secondary amines. So I'm going to give you this reagent here where we have this basic primary amine in H2SO4. Okay? This is a weak nucleophile. This is a weak electrophile. Can they react with each other right now? No. What can we do to make the reaction go forward? Yes, protonate the carbonyl oxygen to make this an activated carbonyl. Now, is this amine able to attack the carbonyl? Yes. Attack, pop the one onto the oxygen, get this tetrahedral intermediate. Okay? Now, this is our intermediate here. This is the new bond that we created from this carbonyl carbon and nitrogen right there. This nitrogen is attached to its R group and 2 hydrogens, and because this nitrogen has 4 bonds, it's positively charged. Now, I want you guys to keep in mind these 2 points here when you guys do the proton transfer steps, right? You want to deprotonate the group you want to keep, and you want to protonate the group you want to kick out. Okay? Because Is this a good or bad leaving group right now? Good leaving group. Is this a good or bad leaving group right now? Bad leaving group. That's not good because we want to keep this new group that we just added and we want to kick out that group, the old group. So luckily for both leavings and helix, they allow you to do this intramolecular acid-base reaction, right? Where you proteinate this group and deproteinate this group at the same time. So you're killing two birds with one stone here, right? We want to proteinate this group to convert it into a good leaving group. We want to deproteinate this group to convert that into a bad leaving group, which is going to give us this intermediate here. Right? Now, this is a bad leaving group. This is a good leaving group. How can we kick off that good leaving group? What's going to drive it to leave? The lone pair on this atom goes to make a double bond there and kick out the leaving group to get this intermediate here. What's the last step to get our final product? Deproteinate and neutralize the positive charge oxygen. Which is this imine here with the I. And that's it for the mechanism. The forward mechanism. The reverse mechanism is going to be different, but we'll go over all the reverse mechanisms if we have time after chapter 18. Yeah. To kick out, in the forward mechanism, yes. If you want to go backward, right, water is the one you want to keep, and this is the group you want to kick out. Because if we want to go back to the carbonyl here, we want to keep this oxygen. We want to keep that oxygen right there. So we would then deproteinate this group and proteinate that group to go back to here, reform the carbonyl, kick out that leaving group to get this proteinated carbonyl here, and then deproteinate that to get to the neutral carbonyl here. That's going backward, reverse. After chapter 18, if you have time, yes, because there's a lot to go over still. Leavens, I don't think so. For 8B, I don't think she went over the reverse. Yeah, I think she just went over the forward. Yeah. But for helix, what in 18B, you guys do need to know the reverse for sure. Right.
So for Imines, we always do an intramolecular reaction to keep that good to make it a backward.
Yes. This intramolecular acid-base reaction is killing two birds with one stone. We're making this a good leaving group and making that a bad leaving group at the same time. We can deproteinate this group with HSO4 minus that we formed at the beginning, and then we could proteinate this OH with H2SO4. But that's two extra steps that you have to draw out. You don't have to do that, right? Nisiri, you had to do that, right? If you did this kind of step here, Nisiri would take off points on the exam. But luckily for helix and leavens, they allow that intramolecular acid-base reaction. Yeah. Yeah, these two electrons here on the nitrogen are going down to make a double bond right there between this carbon and nitrogen right there, right? Because this bond here has two electrons. Those two electrons are coming from that pair of electrons right there. But that carbon is going to have 5 bonds when we do that. 1, 2, 3, 4, 5. To conserve the octet rule, we kick out this good leaving group that we just formed, which is this water here. And for leavens, include that water, because like side products are graded as points as well for mechanism. Okay. Any questions on this mechanism, the forward mechanism, on how we go from a carbonyl to imine? Yeah, the side product is going to be water. Yes, just water. The H2SO4 here is a catalyst that gets reformed if you use the H2SO4 thing, but yeah, water is just a side product. Yeah. Mm-hmm. For synthesis, no, you don't have to write the side products. For mechanism, he probably won't grade the side products. He'll probably just grade the main thing. Yeah. Yeah.
Oh, just for clarifying, so in Imine and Enamine formations, the side product is like basically the OH detached from the original alcohol.
Yes, this oxygen of the carbonyl here will completely detach off. This oxygen here is that oxygen of the water right there.
Okay.
Because if you follow it along the whole mechanism, that's that oxygen right there.
I
Yes.
got it.
Mm-hmm. Yes. It can if you want to, right? But before that, you have to deprotonate this first, because if you protonate this with H2SO4, we're gonna get two formal charges in this molecule, a positive charge here and a positive charge there. That's very unstable, right? If you want to do it one by one, you first gotta deprotonate this to make it neutral with H2SO4 minus, and then you protonate this after with H2SO4 to get to the here, right? You can do that if you want to. Yes, to save time on the exam. Yeah, you get to choose. You could do the long way or you could do the short way like this. Yeah. Mm-hmm. Yeah. And for leave-ins as well. Yeah. Okay. Let's move on to enamine. So let's say I have this carbonyl and I have this secondary amine right here with H2SO4. What would be the very first step here?
The double bond oxygen over there would attack the uric acid to grab it out.
Yes, protonate the carbonyl oxygen to give us this intermediate, which is an activated electrophile, a strong electrophile. What happens next? Yes, nitrogen attacks. What other arrow happens? Pop the double bond onto the oxygen, neutralize it, create this tetrahedral intermediate. What happens next? Intermolecular acid-base reaction, kill two birds with one stone, make this into a good leaving group, make this into a bad leaving group, like that. Okay, what happens after? Yes, form the iminium bond, carbon double bond nitrogen, kick out the leaving group that we just formed to get this intermediate here. Water side product. What's the problem here? Like, why is this mechanism not going to be the same as that mechanism that we did earlier? What's the difference between this and that? Yeah, there's no hydrogen here. So we cannot deprotonate this nitrogen because there's no hydrogens attached to the nitrogen right there. So we have to figure out another way to neutralize this positive charged nitrogen. E2, yes. That reaction is E2. So I'm going to draw out a hydrogen coming off of the alpha carbon right there. Use HSO4 minus as the base to grab that hydrogen, make a double bond here, and this is going to be my leaving group. It doesn't entirely leave the molecule because there's a double bond right there, but we're going to pop the double bond onto the oxygen to create our enamine, which gives us our neutral nitrogen with alkane nearby. So the mechanism for enamine and imine formation is the exact same all throughout up until the last step. Because the last step here for the enamine, we cannot deprotonate the nitrogen directly. There's no hydrogens there, there's no protons there. To neutralize it, we do an E2-like mechanism where we bring in the HSO4 minus base to grab that alpha hydrogen, form a double bond there, and kick off that leaving group to get this enamine here. For leave-ins, a vocab question for something like this would be like, I'm trying to think about leave-ins mindset and what she wants you to know. What kind of reaction would neutralize the iminium ion from enamine formation. Right? Acid-base reaction, E2 reaction, SN1 reaction, SN2 reaction, hydrolysis reaction, E2. Yeah, something like that.
So basically, in this, you get the nitrogen that it kicks off, and then it just gets goes right back up.
Right, because this bond here has 2 electrons.
Right.
Those 2 electrons are gonna go onto the nitrogen like that.
Sure.
That makes that nitrogen neutral now because
Right.
this nitrogen no longer has 4 bonds. It has 3 bonds and a pair of electrons.
Yeah,
Neutral.
Just do an elimination. Right?
Yes. Just do elimination. Correct. Yeah. Yes. Yes. What if there was a? Oh, yes. There has to be hydrogen right here. If there's no hydrogen there, like let's say there's butyl here and a benzene right there, we can't neutralize this anymore. This is our final answer, right? Which is most likely not going to stay there. It's most likely going to go back to this form because this is more stable. You write out this product here with the positive charge nitrogen, right? If this was predicted product, which most likely will not, but that's a good conceptual question, right? Because we need this alpha hydrogen here to make it neutral. If we don't have it, we can't make it neutral. Yeah.
Would it still be considered a major product if it's got to go back?
No.
Okay.
Yes.
He only ever wants us to write out the. I mean, he probably won't give it.
Yeah, he probably won't give it to you. But Levens, like she would like give something like this because for her questions, she likes to put charges sometimes with a negative charge or a positive charge. Right. I know. Tricky. She's tricky with the pKa stuff for sure because Levens loves her pKa values. Yeah. I know. No card. No card. Yeah. I know. Okay. Let's move on to Wittig reaction and Baeyer-Villiger reaction. Yeah. Okay.
No, I took.
This is still chapter 17.
No, it's always like good.
Yeah,
I stay up too, bro. That's what I do, bro.
Okay.
Oh,
Yes, Wittig and Baeyer-Villiger. Yes. Cis and trans E and Z. Yes.
I need some energy, Brian. I need some.
Some energy.
No.
Let me go drink some of this.
I need some high energy.
Some high energy. Yes. I know. I think someone was giving out herbs earlier, but they ran out. Yes. Take a quick 5-minute break or keep going. 5-minute break. Okay, 5-minute break. 5-minute break. Yes. Let's go. Okay, let's continue. So for Wittig reaction, we're gonna have
How do you say Wittig reaction? How do you say Wittig reaction?
carbonyl
How do you say Wittig reaction? Wittig.
plus unstabilized ylid is going to give you a Z alkene. A carbonyl plus a stabilized ylid is going to give an E alkene, right? So let me show you both scenarios. If I have this carbonyl here, and I have this ylid right there, right? When they react with each other, that's the only reagents that you're gonna see. And this is my carbonyl here. This is my ylid right here. When you see a carbon, double bonded to PPH3, right? But another way of drawing this ylid here is this right here. So positive charge like that, right? Okay. This right here is an unstabilized ylid. Right? Because this negative charge here cannot do resonance with the entire molecule, with the rest of the molecule. This is an sp3 roadblock, so we can't do resonance right there. Right? And because this is an unstabilized ylid reacting with the carbonyl, we're going to form a Z alkene. And this is what I like to do. I like to locate my carbonyl carbon. So let's say that's the red carbon right there. And then I like to locate my ylid carbon, which is my blue carbon right there. Right? In the mechanism, the carbonyl is going to go away. This PPH3 is also going to go away. So I'm going to add this group right here so that we can make an EAZ alkene. Right? If this is symmetrical, we cannot have an EAZ alkene. So let's draw in that backbone right there, like that, and have this be the red carbon right there. Now I'm going to make a double bond between the red dot and blue dot right here. Right? This is going to be the new bond that forms where the carbonyl goes away, the PPH3 goes away. Now, because this was an unstabilized ylid, I want to make a Z alkene. This blue dot here is attached to a ethyl group. Now, if this is a Z alkene, do you want to draw the ethyl group going here or here for the Z alkene?
Towards the left.
Towards the left, yes. On the same side, yes. Yeah. Yep. So here we have a carbonyl reacting with an ylid. This is the red dot, the carbonyl carbon. This is the blue dot, the ylid carbon. We're going to make a double bond between the red dot and blue dot. The carbonyl goes away, the PPH3 goes away. This ylid here is unstabilized because this cannot do resonance with the rest of the molecule. There's no carbonyl here, there's no alkene there, there's no benzene there. So this is unstabilized, it cannot do resonance. That would lead to a Z alkene. So because this is a Z alkene, I know my blue dot is attached to an ethyl group. So that's why I'm putting the ethyl group this way to create the Z alkene. I'm not putting it here because that would create the E alkene. E, right? Because if I make a line,
I just want to see how the E looks like.
yep, the E would look like this. Right? The reason why is because when you make a line through the double bond, this is the highest priority group on that carbon, this is the highest priority group on that carbon. They're on the same side for the Z alkene. For the E alkene, they're on the opposite side of the alkene, right? But this is not our product because we're creating the Z alkene since we have an unstabilized ylid. This is our product right here. Okay. Now, if I have something like this, and I react them together, this ylid is now stabilized. This is a stabilized ylid. Because of resonance, yes. This alkene of the ylid here can shift over to make a double bond there, shifting this double bond onto the oxygen right here, making it stable, right? And because it's stabilized ylid, we're gonna go for the E alkene, right? So let's do the same trick. Locate the carbonyl carbon, which is the red carbon here. Locate the ylid carbon, which is this blue carbon here. Make a double bond between the red carbon and blue carbon. And that's gonna give us this right here. Where this is the red carbon, this is the blue carbon. And because I want to make the E alkene, where would this ketone attached to the blue carbon be attached to? Would it go up or down? It would go down, like this. Because if we create a line through the double bond, if you look at this carbon here, the highest priority group on that carbon is this ketone compared to that hydrogen right there. If we look at this carbon here, this group is the highest priority group compared to this group here. The two highest priority groups are on the opposite side of the double bond, making it the E alkene. So that's the Wittig reactions and the different scenarios you can see. The mechanism is a note card thing, so to save time, I'm not gonna go over the mechanism because that's a note card thing. I can if you guys want me to, but we're gonna move on to Baeyer-Villiger. Yeah.
Is that good to panic right now? Because I have never heard about that on the 8B.
No, 8B, don't worry about that.
Okay.
Yeah, don't worry about that. Eventually, we're gonna go over Aldol though, Michael edition. So that will be 8B stuff. Yeah.
Stabilize. It's stabilized because it can't do resonance.
Unstabilized cannot do resonance. Stabilized can do resonance, right? Because this alkene of the ylid here can do resonance with the carbonyl, and resonance is a stabilizing factor. So that's a stabilized ylid, leading to the E alkene.
Trans product.
We can't say trans because trans and cis are only used for exactly two substituents on the alkene. This alkene here has three substituents. This substituent, and this substituent here. So for nomenclature, trans and cis is only used for two substituents. So that's trans, this is cis. Exactly two substituents. Right. You could also say this is Z, this is E. Right. Yeah. Okay. Yes.
The bottom structure for A is not a valid resonance. Oh, I mean like
A, yeah, this is a valid resonance structure, but it's only resonance within the ylid itself. This ylid here cannot do resonance with the rest of the molecule, so it's unstabilized ylid. Whereas this ylid here can do resonance with the rest of the molecule. Another example of a stabilized ylid that you can see is something like this. Right, where this ylid here can do resonance with the molecule like that.
It's all conjugated, right?
Conjugated, yes. Another example is that as well. This is also conjugated like that. Yeah. Uh-huh. Okay. Now, any questions on Wittig before we move on to Baeyer-Villiger? Oh yeah, you can move myself. Yeah. Yeah, let's move it right here.
thank you so much.
Uh-huh. Yeah. Of course. Okay, let's move on to Baeyer-Villiger. Okay. Baeyer-Villiger. So we're gonna have, I'm gonna just give you guys a lot of examples, and it's just gonna click after we do these examples here. If I have this carbonyl here, which is that, and we react it with some peroxy acid like RCO3H, we're gonna insert an oxygen between the carbonyl carbon and one of these groups here. But to do that, we need to know the migratory aptitude list. And hydrogen, I know for sure, is the first one, but I'm not sure of the rest. Like, can you guys check for me what the migratory aptitude is? Tertiary is probably the second. I see. Phenyl. Okay, got it. Thank you. Right, so this is the migratory aptitude list right here. So when you see this carbonyl carbon right here, look at the nearby carbons. We have a tertiary carbon here. We have a primary carbon here. Right? Ignore the bond to the carbonyl carbon. We're not counting that carbon. Count the other carbons. This carbon here is attached to 3 other carbons, 1, 2, 3, making that tertiary carbon. This carbon here is attached to one other carbon, making that primary carbon. And based on the migratory aptitude list, the tertiary carbon is higher priority than the primary carbon. So we're gonna put the oxygen right there, like this. And that's the final answer right there. We insert an oxygen between the high priority group and the carbonyl carbon, right? This was the red carbon right here, and the blue carbon that we chose was the tertiary carbon, which is right here. We inserted an oxygen between those 2 carbons right there as the final answer. Right. Now I'm gonna give you guys multiple practice problems to try out here, and we're gonna. Look at this right here. Okay, try these 1, 2, 3, 4 problems out for Baeyer-Villiger, and I'll come around and answer any questions you guys have, and then we'll move on to the 2 tests, Failings test and tolerance test for chapter 17, and we'll be done with chapter 17. Oh my gosh. Yeah. Yes. Oh, hey, Madison. Hey, going well. How are you? Oh, yes. I need to give you the hoodie. Yes, yes, yes.
So we were doing practice with alcohols,
Uh-huh.
and so is this one gonna be like you just attack it? Would it be SN1 or SN2?
So when this alcohol gets protonated by the HX, that becomes OH2 plus.
Yeah, and then it leaves a
Carbocation.
yeah.
And then you stop there and you look for any rearrangement steps that you can do. Because this is a secondary carbocation here, nearby is a secondary carbocation, this is a primary carbocation, we don't do any hydride shifts because this is the most stable carbocation we can have. So then the I minus comes back to attack the carbocation to give us our final answer. This methyl group there is still there as a wedge. It stays the same.
Okay,
Yeah.
so the only stereochemistry that changes is what's over here. It becomes planar.
It becomes planar, right? And when the I minus attacks, it can attack on the top side, giving you a wedge product, or the back side, giving you a dash product.
Okay.
Yeah.
Okay.
Yeah. See you, Maggie.
Thank you
Bye.
so much.
Of course.
And I had one more question. On the back, I tried to do. Okay.
Yes.
This, I don't know if I did it right.
Oh wait, I think this is supposed to be water, right? Because like if you have acid and OH is minus like that.
Water. It is.
Yeah, because this is supposed to be water. Yeah. So try this again. Try this again.
Oh, so it changes the whole thing.
It changes the whole thing because this wouldn't be OH. This would be OH2 plus, and then that would change up the whole thing. Because when this is OH2 plus, you would not do that, right? Because this is a bad leaving group. You would do the intramolecular acid-base reaction. Convert this into a good leaving group. Convert that OH2 plus into a bad leaving group by deprotonating this group and protonating that group at the same time, right? And then you can kick it out. So try it again. Try it again.
So if it was OH minus, would this be right?
No, because the OH minus would react with the H2SO4 to create water. Acid-base reactions, the fastest reactions can happen first.
Okay.
Wait, let me give you your hoodie right now, Maddie. And then let's take a picture right now. Can you take a picture for us, Maddie? For Jenna?
Yeah.
Thank you.
Sorry.
Yes.
I guess the fourth one.
Uh-huh.
Do we put it somewhere here?
That is not directly attached to the carbon, no carbon.
Oh, so it needs
So
to
no.
be like one of these.
Yes, you could compare that carbon with this carbon right there.
Is this one what's the alcohol like OH?
Let me see.
Number 3.
Number 3. It's gonna become OH, but the overall thing is to be carboxylic acid when the OH is there because it's next to the carbonyl.
What?
Like if you, yeah, it is an OH, right? But it's not an alcohol. It's considered a carboxylic acid.
Oh, carboxylic acid.
Right.
Oh,
Because it's next to the carbonyl.
OH,
Yeah, right. But you're right. There's gonna be OH right there.
Oh,
And this is not a primary carbon. It's not attached to any other carbon, right? It's a methyl. It's a CH3. Yes.
So how wait?
Oh, and that's the worst one.
Yes,
oh,
that's the worst one.
Isn't it like a why is it not a primary?
So we're gonna ignore the bond to the carbonyl carbon.
So is this a specific subset where we take
in
on
that
this
case,
new
this
rules,
is primary.
new outlook on the primary, secondary?
No,
tertiary?
yeah. What
Yes,
he's
yes. New
saying-
outlook.
he's
Yes.
saying for these examples to completely ignore this.
So in that case, this is primary.
Yes,
right?
that is primary because you're just looking at that one carbon right there.
So we don't count it in general, or for just for this?
Just for
in
this.
this
Just for
project,
this.
just
Just
for
for
this.
this.
Special out.
For Baeyer-Villiger. Yes. Yes, Alicia.
Oh, I'm working on this one.
Yeah.
So I'm thinking we don't want this one because this one's a metal, but I think it's right here that we add the O.
Yes, correct.
But I don't know how we can.
And you know how this is a 5-membered ring right now?
Yeah.
When we put that O right there, it's gonna become a 6-membered ring. Right? So try drawing a 6-membered ring, but oxygen is part of the ring right there. And you could also number it 1, 2, 3, 4, 5 to see how things change. Right? And I'll come back and check what you get afterwards. But you're gonna get a 6-membered ring, but oxygen is part of the 6-membered ring in the product. Okay, yeah, of course.
Oh, you put it right here.
Like not even a primary.
It's methyl because you ignore that one. It's attached to 0 carbons, so it's Me methyl.
And then this is it like we're looking at it from here. So that's
Yes, that's a primary carbon. So you're comparing a primary carbon with a methyl carbon.
okay, and I would insert it here.
Yes, correct.
Oh, I know we're gonna go over it right now, but like, am I on the right path?
This phenyl group is higher priority than methyl, that's good. But you're comparing a hydrogen with the tertiary carbon. Hydrogen has higher priority. Hydrogen is the first one.
Oh.
I know. Yeah, that's a tricky one.
So for this carbon over here, right? We don't count this.
Yes.
So this one is only attached to 1 carbon here. So this is gonna be primary. But this carbon over here is attached to 1 carbon here, 1 carbon here. So this is 6.
Oh, sorry.
Like, did I like structure?
Yes, that's right.
Okay.
That's the carboxylic acid right there. Yes. Madison, you wanted the extra large one, right? I couldn't find the extra large one. Let me see here.
Do you have a large too? Whatever. I just didn't know what like how they sized out.
Yeah. I ordered 2 extra large. I already gave 1 extra large out, but I can't find the extra large one unless they messed up the order.
No, this is it.
Oh, that's extra large right there.
Yeah.
Okay, that's good.
Is that a large?
These are the 2 medium ones.
Oh, those are medium.
Yeah.
I'll take that.
Okay. The hoodie. So I made them from got them from Custom Ink. One hoodie is $60. $60. $60.
That's a
But
robbery.
it's Custom Ink. I know. When I do bulk order, it gives me a discount though. So luckily I did a bulk order, so they gave me a discount. Yeah.
$6.
60. I know. It is. Yeah. Yes. Let's take the picture, Madison.
Jenna has a matching one too.
Yes.
Jenna
We could take a
and
picture
Riley.
together. Oh, Jenna, yes. Jenna and Riley, they have the,
they have
the matching
She
one.
always wears it to work. I'm like, oh, okay.
Oh, really?
Yeah.
Oh my god.
Yeah.
Let me go get mine so that we can take the picture together. Let me
Okay.
get my phone too.
Oh, yeah.
Yeah. Okay.
Yeah, okay. Oh my gosh. 1, 2, 3. 3 Oh, wait, so it's still 6-membered, right? I mean, it's changing into a 6-membered.
Yeah, 6 members.
That doesn't sound like a
Did you have them last year? Did you have them when it's
Yeah. And then this is where the other one is.
Yeah.
I'm going to go back and check that I did. There's no hydrogen on any of the other ones, right?
You were there last time. And that's when I got
You saw what you check right?
Yep, that's one.
I mean, I saw him screen recorded, so I didn't know anything about that.
Oh, it's going. It's going. Yeah, I saw you cooking on that whiteboard over there.
Yeah, I understand all the materials for
Awesome.
most of the materials.
That's awesome.
Since like it's one.
You don't happen to be doing that.
I
I slept
got
on my alarm. And I missed my 5th quiz.
Didn't I talk about this? About being worried about my alarms?
I don't remember. I've had this conversation with so many people. No, because I set my Fitbit alarm. Because I
So
don't
you
want to
gotta
wake up.
set 2 alarms.
Yeah, but I don't want to wake up my roommate at 7 in the morning. And so, yeah, I do. So I always set my Fitbit alarm, and it's worked the last 4 times. So I'm like, oh, whatever, I'll just do that again. And I completely slept.
Okay,
there.
so
So much.
I'm gonna write the answer for these problems and then let me know if you guys have any questions so that we can move on to chapter 18. I'm gonna skip the failing test and tolerance test because that's note card reaction. No mechanism there. Okay? So we're gonna do this right here.
Oh, fake Golden Gate?
Right.
Oh, that's real Golden Gate. It's San Francisco. The sack has the fake one.
So it was.
Okay. Did you guys get these as your answers? No?
It'd be cool to be up here. I want to do it. I want to do it again. But we'll see. I might be traveling, so we'll see what ends up happening. Yeah, I like it as well.
Oh, Woodland Hills? It's pretty fun.
Yeah.
Will an H on the end always make it OH?
Yes. When you have an
Always
H,
get carboxylic acid.
yes, every time. When you have an H, always carboxylic acid. Mm-hmm.
Oh, yeah, when it's H carboxylic acid.
Yes. Think of that as oxidation. That's another way we could
Those
oxidize.
are easy ones, though. You just slap the O on.
You just slap the O on, yes. Mm-hmm.
This one's easy.
You just gotta know this though, for sure.
What is pH?
pH is phenol. This is pH.
Oh, okay.
pH versus methyl.
Can you explain the second to last one why you put? Because I put the open here because I thought this was like more substituted.
This is more substituted, but it's not directly attached to the carbonyl. This is the carbon that's
it has
directly
to be
attached to the carbonyl. Yes. Mm-hmm.
Okay.
Yes. Right.
So cute.
So between like.
That was the trick when I was creating that problem. Yes. Mm-hmm. That's why I put that there because I wanted to trick you guys.
Either here or here.
Yes.
Okay.
Yes. Well,
Thank you.
of course. Yes.
For this one,
Uh huh.
Less than 2 hours.
I got this.
An hour and 59 minutes.
Why did you
Mhm.
choose? Why did you choose this one instead of that one?
For this one, this is secondary for sure because it's attached to two carbons besides the carbon. This is primary
Oh wait.
because you ignore the bond to the carbon.
Oh, so okay, that's why.
Yes. And for the ring,
I did that wrong.
right?
Yeah.
This oxygen here is inserted between this carbon and that carbon. That ethyl is not attached to that carbon. The ethyl would be attached to that carbon, but you expand the ring. This is a 5-membered ring. We're gonna get a 6-membered ring. Yeah.
And then you won't ever have like if this is attached to the carbon, it will always be attached to the carbon. We would never like. I kind of just replace it, if you know what I mean. So whatever is attached to the carbon would never leave.
Yes.
It would always be there.
It will always be there. I always made the same mistake too when I first learned this reaction. Yeah, so that's good. Like making the mistakes now, so then you avoid them during the exam. That's good. Yeah.
Sounds a good strategy.
Okay.
It looks like I have like almost 12 minutes. This looks like
Okay.
Oh, okay, that makes sense.
I don't know how much time I want to spend in the basement.
It wasn't a plan, but it worked out.
You also like that?
Are you on the freshman?
It's like, oh,
Taking this class?
That's awesome.
I knew it. I was like, what would happen if you had
Don't look at me like that.
equal
Don't look at me like that.
no reaction?
Mixed products.
Mixed
Mixed products. If it's asymmetrical, if it's asymmetrical, mixed. Yeah. If it's symmetrical, it'll be the same. Yes.
Like there would be both additions of the oxygen.
Yes. If it's asymmetrical, yes. And that would lead to different products. But if it's symmetrical, like the same R group on both sides, you get the same products either way.
but you wouldn't have one with like 2 oxygens are added. It would be like one on
This is
one
just only one
side and then the other product would be one on the other.
Only one, yes.
Oh, okay.
The mechanism for this one is very weird, but I'm not gonna go over it.
Are you supposed to learn it?
Yeah,
Is it actually
it is. He went over it, and it's a no card thing. No card thing. So half sheet, half sheet. Chapter 18.
What about Costco in Oregon?
Aldol addition, condensation, Michael addition, Robinson annulation, L2O4 addition. Okay. The final stretch. The big five for chapter 18 is going to be Enolate alkylation, Enamine alkylation, Aldol addition or condensation, Michael addition, Robinson annulation, and then 1,2 addition, 1,4 addition. So that's like the big reactions for chapter 18. Right? So this is the Enolate chapter here, where this is a ketone here. If I put a strong base like ethoxide, Helix's favorite base, right? He tends to use a lot of strong bases like that. Ethoxide. It's very easy to draw like that. Yeah, right? In chapter 17, we said that this strong base is going to directly attack the carbon and pop the double bond to oxygen, right? But that's a slower reaction than this reaction here. This alpha hydrogen here is very acidic, right? And acid-base reactions are very fast. They're one of the fastest reactions in no-chem. So this strong base here is going to grab that hydrogen, make a double bond there, and pop the double bond to oxygen to give us this enolate ion here, where we have an alkene next to an O- right there. The nucleophile is not this O-, even though it looks very nucleophilic because there's a negative charge right there. We're not going to use that to attack an electrophile. We're going to use this alpha carbon right here as the nucleophile. The reason why is because if you draw out the resonance structure of that enolate ion, that is what we get. And we see that the negative charge on the carbon is less stable than the negative charge on the oxygen. And because the negative charge is less stable on the carbon, it's more reactive at the carbon. So that's why the alpha carbon is the nucleophile, the more reactive atom, compared to the oxygen, right? So that is going to give you this enolate ion here, where my starred atom is the alpha carbon here, right? And that can be used to attack electrophiles or an acid, right? So this is what we do, like alkylation of an enolate ion. So if I have this enolate ion here, and I give it a haloalkane like this, I said earlier that this alpha carbon is my nucleophile, the starred atom. This carbon here is attached to the bromine, which makes this an electrophile. So we're going to do an SN2 reaction here, where the nucleophile is this enolate ion, the electrophile is this primary haloalkane. So we're going to reform the carbonyl, which is going to break the octet rule for this carbon, because it's going to have 1, 2, 3, 4, 5 bonds. To conserve the octet rule, we know that this double bond here can go onto the carbon, giving that carbon a negative charge. But to save time on the mechanism problem, we don't have to draw that mechanism out. We know there's a negative charge over there already, which we could directly attack the carbonyl carbon and kick out the good leaving group right away, like that. And that's going to connect the star and dot carbons together, which is going to be this right here, where this is the starred carbon, this is the dot carbon, this is going to be the new bond between the star and dot carbon, and this dot carbon here is attached to a CH2 isopropyl group. It's no longer attached to the bromine because we kicked that bromine leaving group out. And we see here that we alkylated the alpha carbon, right? The alpha carbon is the first carbon away from the carbonyl carbon. We added that alkyl group there. So this is alpha alkylation or enolate alkylation. So this could be shown in predictive product problem or synthesis problem, or even mechanism problem as well. Yeah. But most likely the mechanism for chapter 18 is going to be like Robinson annulation or Aldol condensation for chapter 18. Yes.
I just don't understand why that reaction couldn't work in the ketone form.
In the ketone form, right here, if I have a ketone like this, and I have this haloalkane right here, there's no nucleophile present, only electrophiles.
Yeah, the carbons are electron donated.
This is an electrophilic carbon. This is also an electrophilic carbon.
Oh, I see.
There's no nucleophilic carbon. Right. We can make this nucleophilic by deprotonating the alpha hydrogen to create the enolate ion, which creates our nucleophile right here. But this and this will have no reaction. Electrophiles do not react with each other. Yeah. Yeah, these two are different problems. Like you see these together, no reaction. Yeah, the top reaction here forms or generates the enolate ion. And then when you see a second step of the haloalkane, you could alkylate the alpha carbon like that.
For a predictive problem, how would you give, like, will you put those two above each other under the alpha?
Yeah, so it's going to be like this.
Oh, I see.
Like that, right? Yes. Right, because if you want to do Grignard, right, we have to make it MGBR here and put a bromine right there. But it's going to be very hard because there's a carbonyl here. If you put an MGBR here, it's going to attack itself, right? This one right here? Yeah, it would be different. Like, yes, this is going to be alkylation, but because we don't do Grignard because of the carbonyl present right there, right?
Oh, you want to keep the carbon? Oh,
yeah, we want to keep the carbonyl. When we do Grignard, we don't have a carbonyl. Yeah, we destroy the carbonyl. Yeah, we destroy it. Yeah, we want to maintain the carbonyl. Yeah. Okay. Yes. The ROH is a solvent. It's not going to do anything in the mechanism. It's just there to facilitate the reaction, right? Because this alkoxide ion here cannot exist like by itself, right? It has to like float or swim around somewhere, which is this product solvent right here. the neutral version of that nucleophile or base. Yeah. Okay. Now, this could be shown in an explanation problem, right? Because even if you have this right here, if you have excess amount of base, we can deprotonate another alpha hydrogen and generate another enolate ion if we have excess base. And if we have excess haloalkane as well, we're gonna over alkylation. We're gonna do over alkylation, where this is the starred carbon, this is the dot carbon, reform carbonyl, star attacks dot, kick out the leaving group, and that's gonna add the R group the second time. This is the star, new bond to star and dot. Dot is attached to CH2, isopropyl, like that. 1, 2, 1, 2, isopropyl, yes. So if this was a predicted product problem, right, this is most likely your answer, 1 alkylation. But this is more for explanation problem. Like, there's a chance for it to over-alkylate if there's excess base and excess haloalkane, right? That's why we use enamine alkylation over this, because it's more selective. It prevents this over-alkylation, right? So we're going to move on to that preferred reaction next, the enamine alkylation. Yeah, most likely this is going to be your answer here for predicted product, yes. For explanation, this is more for conceptual, like, because if you have excess base and haloalkane, you're going to over-alkylate the alpha carbon. It's going to keep going on and on, as long as you have alpha hydrogens to deprotonate. Yeah. Yes. Levens, I think she did go over enamine alkylation. I think so. I'm not sure, but I think so. Yeah, I'm gonna go over that right now. Yeah. Any questions on this before I move on to enamine alkylation? Okay. And I'm gonna show you guys this in a multi-step predicted product problem, where if I have this ketone right here, and I give you guys this secondary amine with H2SO4. Second step is gonna be this primary haloalkane, and then third step is gonna be H3O plus H2O. This is gonna be enamine alkylation. What do you guys think is gonna happen between this carbonyl and this secondary amine here? What are we gonna form? Enamine, yes. So we went over that mechanism earlier from chapter 17, which creates this enamine right here, where this was the carbonyl carbon, this is the alkene, and this is the amine from that amine right there. Now think of this as the enolate. The nitrogen is not the nucleophile. It's gonna be this alpha carbon right here. Because when you draw resonance, there's going to be a negative charge on that alpha carbon, making that the nucleophile. What happens between this molecule and this molecule here? What will happen between those two? Carbon attacks the bromine, kicking out the leaving group. But what would drive this carbon to what other error has to happen before this? Carbon attacks this carbon. Lone pair for nitrogen goes down to form that iminium carbon, forces this starred carbon to attack the dot carbon, kick out the leaving group, to give us this group here. One, two, three, like that. And we just alpha alkylated the enamine. This is the alpha carbon. We alkylated that alpha carbon. Right? And this is an iminium bond. Not a neutral imine, but an iminium bond, because we have a carbon double bond nitrogen that's positively charged. Yes.
So the lone pair goes down and then the
Right. This alkene right here makes that bond right there. Yes.
Is the alkene driving this attack, or is it the lone pair?
The lone pair is pushing down, forcing the alkene to attack that carbon, kicking out the leaving group. Right. If you just draw the star carbon attacking the dot carbon right away without that arrow, you would have a positive charge on that carbon right there, which would be stabilized by this nitrogen. So I just did it right away, so then we save time. We don't have to draw that resonance structure out. Right? You can do that step by step, but this is going to go straight into the more stable, more major contributor of the resonance structures. Right? Yes. We took the lone pair on the nitrogen to go down to make a double bond between this carbon and nitrogen, but this carbon here is going to break the octet rule if we don't do anything else, right? Because this carbon here already has 4 bonds. If we try to make a double bond right here, that carbon is going to have 5 bonds. 1, 2, 3, 4, 5. So to conserve the octet rule, we know this double bond is going to have to pop onto the carbon, giving that carbon a negative charge. The oxygen, there's no oxygen here. There's only nitrogen. Oh, this oxygen right here?
The enamine formation.
Yes, the enamine formation, this oxygen is water now. This oxygen came here. Right. But the mechanism was shown earlier when we went over the enamine formation mechanism. Right. We protonate the carbonyl, secondary amine attacks, and we do that whole process to get to this enamine and kick out the water. You deprotonate the alpha hydrogen with the HSO4 minus, create the double bond, and push the double bond to the nitrogen to make it neutral in the mechanism from here to here. Right, but that's the mechanism that we went over earlier. Yeah. Okay. Now, if you have this iminium here and you put it with acid and water, this is the mechanism we didn't go over, but this is hydrolysis of enamine. We're gonna revert this iminium bond back into the carbonyl. This is the reverse mechanism. Right, that's gonna hydrolyze the iminium bond back to the carbonyl with acid and water. We didn't go over the mechanism of this one. Yeah, but that could be tested, the mechanism for that reaction. Yes, yes. That's why this reaction here, like this chapter is a lot, because you need to do the forward mechanism, reverse mechanism, in acidic conditions, basic conditions. Here, yeah. For here to here, that is hydrolysis of enamine, right? Or the reverse mechanism of enamine formation. Reverse. Because we're not forming an enamine, we're going backward to a carbonyl. Right. Yeah. Which is also known as hydrolysis of enamine. But this overall reaction here is enamine alkylation. Because once we have this enamine here, we alkylated the enamine with the haloalkane. Right? And that prevents over-alkylation because this is not as reactive as the enolate that we formed earlier. Right? This is not as reactive as this, like this. This right here is less reactive. This right here is more reactive. So this one here prevents over alkylation. So that's more of a conceptual multiple choice or explanation problem. The reason why this is more reactive is because we have that full negative charge right there, wanting to make this carbon more reactive. Because this is neutral, this is less reactive, and that prevents over alkylation. So that's more a conceptual question for explanation or multiple choice. Okay. Okay. Any questions on this before we move on to aldol addition, aldol condensation?
Can I ask you how the hydrolysis briefly goes out?
Uh-huh.
I mean, like, you're probably trying to create a leaving group right there, but then how do you get, like, a O double bond?
Yeah, so let's actually go over that hydrolysis mechanism right here. Right. So
If it's not relevant, I don't want to.
it is relevant. Yeah,
Okay.
it would be. It could be tested.
Okay.
Right. This is going backward from an enamine to back to the carbonyl.
Okay.
Yeah. So let me actually go over enamine. Back into the carbonyl.
Oh yeah.
Which is going to be with H2SO4 and water.
Right.
Right. So what's going to happen first? What do you guys think? This is going to be a tricky question here. The first step is very tricky. What's going to get protonated?
That double bond.
Yes.
Because it's very reactive.
Yes. We don't protonate the nitrogen.
Yeah.
We protonate
it's not
the.
satisfied being protonated.
Right. Mm-hmm. Yes, because of the resonance. If we draw the resonance, there's going to be a negative charge on the carbon, making it more reactive, less stable. So the first step here is to protonate the alpha carbon with the strong acid we have. But what drives that is going to make that iminium bond right there. And I'm going to leave the hydrogen as invisible.
Okay.
Now, once we have this is an activated electrophile. We could bring in water to attack that activated electrophile, push the double bond to oxygen to create this tetrahedral intermediate here. Right. Now the pattern is going to be the same. What group do you want to kick out? What group do you want to keep?
You're trying to kick out the amine.
Yes, we want to kick out this group. We want to keep this group. But right now this is a bad leaving group. This is a good leaving group. What can we do to kill two birds with one stone here?
You can do a protonation. Internal protonation.
Yes. Mm-hmm. Internal or intermolecular protonation, deprotonation, acid-base reaction.
Yeah.
Converting this bad leaving group into a good leaving group. Converting this good leaving group into a bad leaving group. And that's good. Everyone is happy now because we want to get to that form right there. Right? Now, what can we do to drive that good leaving group off? Lone pair elimination, carbonyl, kick that out, and we're gonna get this as a side product, that neutral amine, and this protonated carbonyl oxygen with a positive charge, where the final step is gonna be deprotonation with the HSO4 minus to get to the neutral carbonyl. So do you guys notice how the mechanism was the exact same as going forward, right? It's just a different nucleophile. Right? So forward and reverse is very similar. What's going to be tricky here, especially for helix class, is intermolecular, like the intermolecular acetal.
Intermolecular steps right there. One was a protonation, one was a internal elimination.
Yes, this is an intermolecular acid-base reaction, right? But the intermolecular reaction I'm talking about here is like if you have something like this, and you react this with H2SO4 and water. Like this is going to be the tricky one here. This is an acetal because this carbon here is attached to two OR groups, and this is going to go back to the carbonyl, and that's going to be the tricky example there. Yeah. Do you guys want to go over this mechanism as well? Okay. So we know this is an acetal here, and we want to make this carbon here attached to two OR groups to become the carbonyl. So that means that yes, you gotta think about this really quick. What? Yeah, we're gonna break this right here, right? Protonate. Wait, hold on. Because I'm thinking of, do we protonate this oxygen or this oxygen right here? The right one. Yeah, let's try that. Let's see. Let's protonate the right one. That will convert the right one into the leaving group. What can we do to kick that good leaving group that we just formed out?
Another elimination internal?
Yes. Form the carbonyl, kick out that leaving group, and get this intermediate here. And then this ethanol got kicked out. water can then come in, attack the carbonyl, push it up there. But that's gonna go to a hemiacetal, and that's less stable. So we don't want that. Because once we deproteinate this here, that's less stable. Let me proteinate this oxygen instead. This is not gonna be major because we're going from an acetal to a hemiacetal. That's not favorable. So I'm gonna proteinate the other oxygen. Right. Now this is gonna go back down. Yes, this is the correct way. Right.
He's trying to see which one to approach first.
Let's make this a hemiacetal. Yes, because this is an acetal right here, and we want to break it open to the carbonyl. This is going to be the leaving group, making this an alcohol. This is going to be carbonyl. We cannot neutralize that because there's no R group there, right? So this is actually not very stable because it's going to go backwards here. So because this is a cyclic acetal right here, that's very stable, it's very hard to go back into the carbonyl. No reaction. Or actually, there can be a reaction. You can open up the acetal, actually, right? But when we do that, we're gonna have an alcohol here, and this positive charged oxygen that cannot be deprotonated, right? So, what was the other thing that we tried? We formed the carbonyl there. That can also be deprotonated. This is more likely a hemiacetal problem. I'll have to see Felix's exams to see what he wants with this. But if this is a hemiacetal, where this is an OH right here, this would be an OH, and now we can deprotonate that oxygen, making it neutral with the HSO4 minus. Right, and that's gonna lead us to this alcohol with this carbonyl right here. And the reason why this is intermolecular is because we have a carbonyl here, and we have an alcohol right there. The alcohol is in the same molecule as the carbonyl. So when we close it, we're gonna get a cyclic hemiacetal. And we said earlier, this cyclic hemiacetal here is stable and isolatable in lab. This is actually stable, right? Usually when we do intermolecular hemiacetal formation, the alcohol is a separate molecule than the carbonyl, right? But because this alcohol here is on the same molecule as the carbonyl, we're doing intermolecular reaction like that. Yeah.
To change that over there to an H, right there. That was step before. You need to don't right there at the end. Is it supposed to be?
Yes, because this oxygen here grabbed the hydrogen from the H2SO4, which is this H right here. This carbon here is attached to the OH, like that. Yeah. Mm-hmm. Okay. Okay.
Right, this is intermolecular hydrolysis.
Yeah, intermolecular hydrolysis of a hemiacetal back to the carbonyl and alcohol. Right. Usually when we form hemiacetal and it's intermolecular, the alcohol is separate from the carbonyl, right? Like we went earlier, right? On the side, yes. But because this alcohol here is on the same molecule as the carbonyl, we're doing intermolecular reaction, which forms a cyclic hemiacetal. Yes. I remember one question on his exam cell where he had a cyclic acetal, but they're probably in the same ring. But in this case here that I showed you guys, it was not able to get deprotonated. Right. So this is probably what you're gonna get on the mechanism if he does intramolecular hydrolysis.
I want to know H right there in the section.
Yeah, this is an OH. It grabbed the H from that strong acid right there.
Oh, gotcha.
H2SO4. Yes. Oh my gosh, it's 5:40. So I could go over like 2 more reactions. You guys want to go over Aldol and Michael and Robinson? Let's do that. Let's do Robinson because Robinson is a combination of Michael and Aldol, and then we'll end the session. Yeah. Yeah. Okay. Okay. Here's a chart that I'm gonna give you guys to tell the differences between those reactions right there.
I was gonna ask for like
the chart.
because they're all like some of them are 1, 2, 1, 4. Then you have like the 1, 5, like
Uh-huh.
dicarbonyl or whatever.
Yes.
Michael addition is 1,5 always.
Michael's always 1, 5.
Yeah.
Yeah.
1,5 dicarbonyl. Yes.
Huh?
No, that's so real.
Oh yeah.
The nucleophile for these two reactions right here is going to be enolate ion for both reactions. The electrophile for aldol addition or condensation is going to be the carbonyl carbon of an aldehyde or a ketone. Most likely an aldehyde, unless it's intramolecular aldol. The electrophile for microaddition is going to be the beta carbon of an alpha, beta, unsaturated carbonyl. The product for aldol addition is an aldol, which looks like this. The product for aldol condensation is an alpha, beta, unsaturated carbonyl, which looks like this. The product for microaddition is a 1,5-dicarbonyl. Which means that you have two carbonyls, 1,5 to each other. 1, 2, 3, 4, 5. Right? Where this is 1, 2, 3, 4, 5. 1,5-dicarbonyl. Robinson annulation is going to be two reactions. The first one is going to be microaddition. And then sometimes, most of the time, actually, you could do an intramolecular aldol condensation. Right? And for aldol condensation, you're going to need high heat, high temperature. When you have 0 degrees Celsius, that's low heat. You're going to stop at the aldol addition. Right? And you also need a second alpha hydrogen for aldol condensation. But here's like the chart of the differences in the nucleophile, electrophile, and product for aldol addition, condensation, and microaddition. Robinson annulation is a mixture of both reactions. The first step is microaddition. The second step is aldol addition, condensation.
Does Michael need heat or is that at?
Michael does not need heat. And there's 3 types of aldol, right? 3 types of aldol. There's self-aldol, there's mixed or crossed aldol, and there's intramolecular aldol. Right?
Self and intramolecular are kind of similar but their self is like the traditional kind of way of doing it with those.
Yes.
canceling out, right?
Mhm.
If you draw the shortcut,
Shortcut.
right?
Right.
If you do Aldol condensation versus addition, you
Uh-huh.
get different. Are you talking about condensation here?
I'm talking about Aldol condensation here. Yes.
Okay.
Let's do Aldol condensation, which is going to be with heat. I'm going to show you guys the mechanism quickly with the basic one.
Sure.
Show you guys how to predict it quickly without doing the whole mechanism to save time on the exam.
Just using the double bond O's and the HH.
Yes. Right. And then after that, do micro addition. Show you the mechanism for that, and then do Robertson annulation to end off the session. Okay. So let's start off with a basic aldehyde, and we have this strong base right here with the alcohol. And let's say we have like excess amount of this. If he doesn't give you excess, assume excess. What's going to happen between this strong base and this structure here? What's going to happen between them? What is the most acidic hydrogen in this molecule?
The aldehyde hydrogen?
Aldehyde hydrogen, you do not want to deprotonate that at all. The alpha hydrogen.
That one's not acidic.
This is not acidic.
Because you have super electron withdrawing carbon.
Yes.
Carbonyl.
Yes. Right. So this strong base here is going to grab that, and you could draw out the full enolate, create a double bond there, pop the double bond oxygen. I'm actually just going to do that because that's how Helix does it and Leibniz does it. So when we do that, we're going to get this enolate ion here. But what's my nucleophile here? The alpha carbon. Because if we form a double bond here, we're going to give a negative charge on that carbon. The negative charge here is less stable than the negative charge here, making it more reactive here. I'm going to bring in a second equivalent of the aldehyde, where this is my electrophile right here. Reform carbonyl, star attack dot, pop the one onto the oxygen. And this is tricky here, because we're now going to connect the star and dot together. This is my starred carbon. Does that make sense so far on how I got that starred carbon when we reform the carbonyl? Right there. This is the new bond between the star and dot. This new bond here came from this attack. This dot carbon here is attached to a hydrogen, invisible. It's attached to a propyl group. 1, 2, 3. It was double bonded to an oxygen, but it's now a single bond O-. And then to protonate that O-, we're going to use the proton source we have, ethanol, to protonate the O- to become neutral OH. Right? And this right here is an aldol. Stop at low temp, which Helix uses 0 degrees Celsius. But because we have heat, which is the delta symbol, yeah, we're gonna continue to aldol condensation, right? So we also need an alpha hydrogen between the carbonyl and alcohol, which we do have here. This alpha hydrogen is very important for this next step. That needs to be there. If it's not there, we stop here, even if we have heat. And he tested something like this before, where people tried to make the double bond here and kick out the OH, but there was no hydrogen there. Like let's say there was a methyl group there, right? You would stop there if there's no second alpha hydrogen. We bring in the strong base to grab that hydrogen, generate the enolate ion, and create an O- there, double bond here, OH there, 1, 2, 3. Now the next step here is to reform the carbonyl, shift the double bond over there, kick out the OH, and get our final aldol condensation product here. And this is an alpha beta unsaturated carbonyl because this is the carbonyl carbon, this is the alpha carbon, this is the beta carbon. There is a double bond between the alpha and beta carbon. That's an unsaturation, right? That's why we call this an alpha beta unsaturated carbonyl, because there's an unsaturation between the alpha and beta carbon relative to the carbonyl right there. That's a good question. The OH here, we always said this is a bad leaving group, but it's able to leave because of the heat added here and we're in basic conditions. We're given enough energy to kick it out, right? Every step here is actually reversible. But don't worry about the free helix. He won't worry about that. No, he doesn't. He doesn't. Yeah. This step here is irreversible though. the last step, because once we kick out the OH minus, it doesn't want to go back. Yes.
If we don't have heat, would we stop at the addition portion right there?
Yes. Okay. Now, do you guys want to see the shortcut way of predicting the product without doing that whole mechanism? Here is the shortcut. Okay, I'm going to erase the whole mechanism. Is that okay with you guys? Okay. So I'm going to erase these arrows as well, so we could do the shortcut. Okay. Assuming excess of this right here, the first thing I do is locate my starred carbon, which is this starred carbon right here, the alpha carbon, right? It has to have an alpha hydrogen for us to deprotonate to make it negatively charged. Then I locate my dot carbon, which is that carbonyl carbon right there. To predict the product quickly, draw out the starred carbon right away. Everything stays the same for the starred carbon. Nothing changes to the starred carbon at all, right? Then I make a new bond between the starred carbon and dot carbon. This is the new bond between the starred carbon and dot carbon. Then I just draw out what's attached to the dot carbon. A propyl group, 1, 2, 3, 1, 2, 3, an invisible hydrogen, and this carbonyl here becomes an OH, right? This is going to be your product if you have no heat, if you're low temperature. This is your aldol addition product. But because we have heat here, we're going to completely get rid of the OH, right? Completely get rid of the carbonyl of the dot and put a double bond between the star and dot to get your final product right there. So that's how you could quickly predict that product, yes, without doing the whole mechanism to save time on the exam. Yeah. Right. So I'm gonna do it again, but with a different aldehyde now. So if you have this right here, I'm gonna show you guys one more time on how to do the shortcut. First step, starred carbon. Second step, dot carbon. Third step, draw out the starred molecule. Nothing changes to that starred molecule. Let's put heat there, so we do auto condensation. This is the starred carbon there. Nothing changes to that starred carbon. Next step, new bond between the starred carbon and dot carbon, right? And now, let's say we want to do aldol addition. There's no heat there. We draw whatever is attached to the dot carbon, which is this CH2 ring. Invisible hydrogen, and carbonyl becomes OH. That's the product if we have 0 degrees Celsius. But because we have heat, we're going to erase that OH and put a double bond right there between the star and dot. And that's our final answer for aldol condensation. And that's how you could predict it quickly without doing the whole mechanism. Right?
Oh wait, so is it alkylation if we add heat?
Yes.
Yeah.
Only for heat.
Only for heat. But let me give you a tricky
Yeah.
example here. If we have something like this, right? And even if we do have heat, let's try to do that again. Star, dot. Draw out the starred molecule. Make a new bond between the star and dot. Dot is attached to invisible hydrogen, isopropyl, and carbonyl becomes OH for aldol addition. Even if we have heat, right? This is still our final answer. We're not going to erase the alcohol and create a double bond there because we cannot create a double bond there. That's going to break the octet rule. If we put a double bond right here, this carbon is going to have 5 bonds. That's not good, right? So heat could be tricky like that. Even if you have heat, you stop here because you cannot create a double bond right there. That's going to break the octet rule like that. So that's the tricky problem there. I've seen him testing that once throughout the quarters, but just keep that in mind just in case it shows up again.
Okay.
Yeah. Okay.
Should we like assume anytime there's like a carbonyl next to like an alkene and like there's resonance that we should be like making sure that the alkene is the one likely attacking instead of the oxygen?
Yes. If that alkene is directly next to the O minus, if it's way far out there in the ether, then it won't do that. Yes. Okay. Now I'm gonna go over mixed and crossed aldol with you guys, but I'm not gonna do the mechanism because I already went over that. But I'm gonna show you guys the shortcut still, just for extra practice. Right. So let's say we have this aldehyde and we have this aldehyde right here, and we react it with the base, right? Now, this is crossed or mixed aldol here. We have star, dot, star, dot. So our 4 different products here could be A, this is A, this is B, A, B, B, A, or B, B.
This is like that 4 possibilities when you get crossing, right?
Yes.
Like 2 different types.
2 different types.
Starting. What's the word? Starting material.
Starting material, right. The first letter here is going to be the nucleophile, the star. The second letter is the electrophile, the dot. So this is self-aldol, this is self-aldol because they're the same color. This is mixed aldol, this is mixed aldol because they're different colors. Right. So
that's a good way of looking at it.
Right. And same shortcut, right? That's the red star, red dot. Done. Right. For the AB, because the first letter is red, that's the nucleophile star right there. Now the new bond is to the blue dot. This blue dot right here. That blue dot is attached to CH2, isopropyl, double bond. BA, this is the blue star, new bond between blue star, red dot. Because this is condensation, I'm going to put double bond right there. Red dot, ethyl, and that's it. Now a self with BEB. Blue star, blue dot. So these are the different aldol condensation products that you can get from this mixed or crossed aldol here.
Yeah.
Yeah.
And then the way you reduce that is that you add, make sure that there's no primary hydrogens, right?
Make sure there's no primary hydrogens.
Alpha hydrogens, alpha protons.
Alpha protons, yes, right. And we can make a double bond here because no octet rule is broken here. If the octet rule is broken, you cannot create that, right?
Yeah.
And you would put a single bond OH there, single bond OH there. But in this case, we can make a double bond there with heat, like that. Yeah.
Gotcha.
Okay. Now that was crossed or mixed aldol, right? I'm gonna go over selective aldol now, right? So that's gonna be something like this.
It was a good one. I took a picture.
Which one is this?
This is selective aldol.
So basically,
Right.
when you add no alpha protons, you have to reduce your possibilities with a mixed aldol reaction.
Let's do actually this right here.
That 4 matrix becomes like
Right. Okay. So
there's no alpha protons here.
there's no alpha protons here, so we have no starred carbon here.
Yeah.
We can't deprotonate an alpha carbon to make it in the nucleophile. These are my only electrophiles right here. My nucleophile is going to be this and this. There's no alpha proton, because you know how when we generate the enolate ion, we have to deprotonate an alpha carbon by taking away the hydrogen of the alpha carbon, right? This alpha carbon here has 0 hydrogens. So this base here cannot deprotonate that alpha carbon. So this cannot be my starred carbon. Same as for this carbon here. We can't make that the starred carbon because we can't make it negatively charged. We can't deprotonate it, right? That's why this is our only electrophile. This is our only electrophile. When we put in this ketone here, these alpha carbons here do have alpha hydrogens to be deprotonated. So those are my starred carbons. And I'm saying slowly add them, right? Because if you excessively rapidly add them, they're gonna maybe react with itself, do self-aldol, but we don't want that, right? We want this to be the start and we want this to be the dot. So if I go over here to predict the product quickly, the products are going to be like this if you do the shortcut. Oh wait, no. This is the dot, that was the star, and the star is attached to that, and that. Right, where this was the star, this is the dot, this is the star, this is the dot. Right, so if you did the shortcut, you would get those products. You could even try that out with the mechanism too. Yes, this is acetone right here. Yeah, for that right there. Right, this is the star, this is the dot. This is the star, this is the dot. Yeah, okay. Okay, now intramolecular is very hard, like harder than the self and mixed aldol, mixed and crossed aldol. Okay, so let's go over that. Michael is relatively easy compared to aldol. So if I have something like this, and I react it with this right here, and I have something like this. Right, this is gonna be 1, 2, 3, 4, 5, 6, and it's gonna be that. Right, and then we do that boom, we do this boom, and we react it with this and this. The mechanism is going to be the same for the self aldol and mixed and crossed aldol. The tricky part for intramolecular is choosing what your star carbon is and what your dot carbon is, right? We have two potential dot carbons in this molecule. This carbonyl carbon versus this carbonyl carbon. Which carbonyl is more electrophilic? Which carbonyl is more reactive, more positively charged?
The one that's not next to a terpene.
Yes, this aldehyde right here. Because this aldehyde only has one R group, whereas this ketone has two R groups.
Yeah.
These two R groups are donating electrons to like carbonyl carbon, making it less positively charged.
Yeah.
This is only like donated by one R group. So
Yeah.
I'm gonna make this my dot carbon right here. So that I know my dot carbon is that. Now, which one is gonna be my starred carbon? Is it gonna be this alpha carbon or this alpha carbon here? Which one can be my starred carbon? The left one, because this has no alpha hydrogens. And because this is intramolecular, I'm gonna make a 1, 2, 3, 4, 5-membered ring, right? I'm gonna draw that 5-membered ring template out like that, where let's say this is 1, 2, 3, 4, 5. My 1 was the star, my 5 is the dot. This is the new bond between the star and dot, the new bond between 1 and 5. The 1 is attached to this carbonyl with the terbidyl. The 3 is attached to the ethyl. The 5, because we have heat, we're going to do aldol condensation, get rid of that carbonyl, put a double bond between 1 and 5, the star and dot, for aldol condensation. The hydrogen is still there on 5, but I'm making it invisible. This one here is trickier. We have two potential dot carbons. This dot carbon, this dot carbon. Which one do you guys think is the dot carbon we're gonna choose here? The one on the right. So if this is our dot carbon here, right? Let's go with that. There's two potential alpha carbons here. Which one can it be if we were to choose one? Is this alpha carbon or this alpha carbon? The right, because it has an alpha proton. If this is my star, this is a dot. How many membered ring are we gonna form? 4. That's unstable. We don't want that. So let's move here. This is going to be my dot, and this is going to be my star or my star. Which one would it be? Yeah, both can be, but this outer one is going to make the more stable ring, because that's going to make a more stable ring.
Are we making 5? 5 or 6?
It's 5 or 6.
5 or 6.
Yes. In this case, we're making a 6-membered ring. So when I draw that 6-membered ring template out, that's going to be this 1, 2, 3, 4. Yes, right. You don't want to make a 4-membered ring, you don't want to make a 2-membered ring or a 3-membered ring.
For the 5 in this case, you choose the 6.
Yes, if you can choose between 5 and 6, you choose 6 over 5 because 6 is more stable than 5. But in this case, we can't form a 5-membered ring. We can only form a 6-membered ring or a 4-membered ring, right? So we would choose a 6-membered ring. Now, once we have that, the 1 is the start carbon, 6 is the dot carbon. That's the new bond between 1 and 6. 2 has the carbonyl, 4 has the methyl, 6 has this phenyl group. And because we have heat, we're going to completely get rid of the carbonyl and put a double bond between star and dot. And in both cases, we get the alpha beta unsaturated carbonyl, right? Because this is the carbonyl carbon, this is the alpha carbon, beta carbon. Carbonyl carbon, alpha carbon, beta carbon. There's an unsaturation between them. So that's how you could confirm your Aldol condensation product as well. Right. I know I'm going faster, but this is all going to be in the recording, so you guys can review what I just did and practice that on your own after. But that's self-aldol, mixed cross-aldol, selective aldol, and intermolecular aldol. Right. The nucleophile is enolate, the electrophile is a carbonyl carbon, and the product is an alpha beta unsaturated carbonyl if you do aldol condensation, or an aldol if you do aldol addition. Right. Okay. Michael addition is a baby reaction compared to aldol. So let's do that Michael addition now. And I'm actually going to go over Robinson annulation as well with this, and then we're going to end the session there because Michael addition goes first, and then intramolecular aldol condensation goes after, right? So let's say I have, before that, I want to explain the reactivity of this alpha beta unsaturated carbonyl here. There's 2 electrophiles in the structure. There's this carbonyl carbon, and there's this beta carbon as an electrophile. This carbonyl carbon is easy to see why it's an electrophile because it's attached to the electronegative atom oxygen right there. It's hard to see why this beta carbon is electrophile, but if we draw out the resonance structure like this, we see that there's going to be a positive charge on that beta carbon, like this. Right? And because of this full positive charge on the beta carbon right there, that's why this beta carbon is the electrophile. There's 2 nucleophiles that I want you to know. There's the reversible nucleophiles, and there's the irreversible nucleophiles. And this will go into 1,2,1,4 addition. So 1,2,1,4 addition is going to use this numbering system here. This oxygen here is atom number 1. This is 2. This is 3. This is 4. That's just convention of the people who found this reaction, right? They labeled this alpha beta unsaturated carbonyl like this, where oxygen is 1. This is 2, 3, 4. Your irreversible nucleophiles are either going to be a hydride ion or R- ion. This hydride ion could be LiAlH4 or NaBH4, reducing agents. This R- here is going to be your organometallics, RMgX, where X could be Br or chlorine, or RLi, organolithium. I've seen in Helix electrolytes, he also gives this, but we don't really see this a lot. But this is also an irreversible nucleophile. The reversible ones would be like your OH minus, your RO minus, your CN minus, your neutral amine. This is the important one, your enolate ion, but the nucleophile here is the alpha carbon. Even the enamine, if you have an enamine, the alpha carbon is the nucleophile. And this new reagent here, organocuprate. Right, and you could see it like this if you, sometimes. Right. These are your reversible nucleophiles that would do a 1,2, no, 1,4 addition, aka conjugate addition. The irreversible nucleophiles are going to do 1,2 addition, aka direct addition. Now, if we talk about Michael addition, and our nucleophile is the enolate ion, and the electrophile is the beta carbon, are we doing a 1,4 addition or 1,2 addition for Michael addition? Yeah, so if our nucleophile is an enolate ion, and our electrophile is, let's say, do you guys need this chart still? Okay, now we're gonna go into Michael and Robinson here. Okay, so let's start off with this carbonyl reacted with this base with the solvent, and we have this group here. What do you guys think is going to happen first between this strong base and this carbonyl? What's the most acidic hydrogen we have in this molecule? The alpha hydrogen. So we're going to deprotonate that alpha carbon to generate what ion? Enolate ion. That generates our nucleophile. But what's my nucleophilic atom? The O minus or the alpha carbon? Alpha carbon. And if this is our nucleophile, and I bring in this alpha, beta, unsaturated carbonyl, we have two electrophiles, the carbonyl carbon and the beta carbon. Which one would be my electrophile if I have this as my nucleophile? Based on the list I had earlier. Would this be a 1,2 addition or 1,4 addition? Would it attack the second carbon or the fourth carbon? 1,4 addition, conjugate addition, because this enolate ion here is a reversible nucleophile, which is going to attack this beta carbon here, not that carbonyl carbon, which is a 1,4 addition. Yes, we can either attack this carbonyl carbon, right, or this beta carbon. If we attack this carbonyl carbon, that's a 1,2 addition, a direct addition. If we attack this beta carbon, that's a 1,4 addition, a conjugate addition, right? And the things that will attack this beta carbon here are reversible nucleophiles. And those reversible nucleophiles include the enolate ion, the CN minus, the OR minus, OH minus, amines, enamines, right? Everything that is not an irreversible nucleophile. If you had an irreversible nucleophile, like a reducing agents, like LiAlH4, NABH4, or organometallic agent, like Grignard agent, or MGBR, or organolithium, that's going to go directly to that carbonyl there, doing a 1,2 addition. But because this is not a reducing agent, this is not an organometallic reagent, we're not going to do 1,2 addition. We're not going to attack the carbonyl carbon. We're going to attack the beta carbon because this is a soft reversible nucleophile, not a hard irreversible nucleophile, right? Any questions on that? On why we attack the beta carbon instead? Okay. Now we're going to reform the carbonyl. Star attacks the dot, push the double bond over there, check the double bond to oxygen. And when we connect the pieces together, this is what we get. This is the star carbon. This is the new bond between the star carbon and dot carbon. The dot carbon here is attached to an ethyl group, single bond, double bond, O minus, OR. Now this is a good sign because our product for Michael addition is a 1,5 dart carbonyl. 1, 2, 3, 4, 5. How can we convert this enolate into a carbonyl?
Get that bond to leave.
We can protonate it with the solvent we have there, right? We're not going to protonate O minus. We're going to reform the carbonyl and have this alpha carbon here grab the hydrogen, check out the OR group to get our 1,5 dicarbonyl. One, two, three, four, 5. That's the end of Michael addition. That's done. Once we have that 1,5 dicarbonyl, if we do Robinson annulation, what's the second step? Yes, intermolecular aldol condensation. So in that case, right, let's say we have heat. What's going to be my dot carbon? What do you guys think? The electrophile. Would it be this carbonyl-carbon or this carbonyl-carbon? Which one would lead to a more stable ring? This one right here? Let's see it. So let's choose this one. If this is my dot carbon here, my alpha carbon would have to be this or this. Which one would it be? The star carbon. The left one. Because that would make a 1, 2, 3, 4, 5, 6. Yes, that would make a stable 6-membered ring. So if we want to draw that template out, that's this 6-membered ring right there, where this is going to be 1, 2, 3, 4, 5, 6. 1 has the star, 6 has the dot. That's the new bond between them. And then everything else, decoration. 1 is methyl, 2 is carbonyl, 3 is methyl, 4 is ethyl, 6 is ethyl. But what happens to the carbonyl if we have heat? Go away and put a double bond between star and dot. And what do we have here? What kind of product is this? Alpha, beta. Unsaturated carbonyl, which is the product of aldol. Yes.
When you were asking us which one's going to be the star, which is going to be the dot. What were the two options again? Either carbonyl, right?
Yeah, to be the dot.
Okay, so if we pick the other one, and then you pick the outer one on the farther,
Right. 1, 2, 3, 4, 5, 6. Yes, that would be the other product actually. You could actually do that as well. Let's try that out. Let me see. So if this was your dot and this is your star, that's gonna make a 1, 2, 3, 4, 5, 6-membered ring. Going this way, it's gonna be 1, 2, 3, 4, 5, 6. Star there, dot here. This 2 is the carbonyl. This 4 is the ethyl. This 3 is the methyl. This 6 is gone. 1 and 6 is there. This 2 here, no, this 6 here has the ethyl group. So in this case, right, this is different than this. Right, so these are your two mixed products here. But for the exam, right, Helix is gonna make it in a way where you only choose one dot and one star. Right, so he's gonna put, they're both equally major here. If this is mixed, yes. But most likely, he's gonna make you choose only one star and one dot. And yeah, in a way that he's gonna do that, right? And to do that, if this was a triple group, this can no longer be that starred. So we would no longer get that. And the 6 carbon there is attached to this group right here. So that would be the final product instead. So Helix is gonna give something like this, where it's in a way where you only get one product like that. I just created this problem out of nowhere, so it led to 2 different mixed products. But Helix is gonna give it in a way where you only get one product, right? So keep that in mind. The tricky part for intermolecular aldol is that you have to choose one star and one dot that would lead to a stable ring like that. Most likely 1 for the exam purposes. But in the case I give you initially, it could give you 2 mixed products. Okay, done. Yes. What time is it? 6:20. Okay. Yes. I know. Yes, of course.